Thank you everyone for coming out this evening. It is my very great pleasure tonight to introduce our speaker, Dr. Rob Jackson. I first met Rob when we were both in graduate school, and I saw him give a talk on root physiology. And in this talk, he showed some data about how plants tended to grow the most roots in those parts of the soil that were most enriched with nutrients. And at the time, there was a lot of question about how plants foraged in the soil, how they sought out resources in the soil. And I remember thinking that his work exactly identified this key gap in our knowledge about how plants interact with the soil environment, and he demonstrated a really insightful way to get the data that we needed to fill that gap. As I got to know Rob better, working in his lab as a postdoc, I continued to admire his ability to identify the most important questions in ecology and his clever experimental approaches to investigating those questions. His work on hydraulic fracturing is no exception. His lab group was one of the first to see what we needed to know about this particular technique, and he is now looking at the data we need, or finding the data we need to address this debate about fracturing, people, the environment, the safety of this technique, and so on. And he's basically providing what we need to know to have a reasonable and informed discussion of this topic. Rob earned his undergraduate degree in chemical engineering from Rice University and 2 master's degrees in ecology and statistics and his PhD in ecology from Utah State University. He has served on the faculty at the University of Texas, Duke University, and has recently moved to Stanford University, where he is the Douglas Provostial Professor at the School of Earth Sciences. He has published over 200 books and articles in peer-reviewed journals on a wide range of subjects, including root biology, the global carbon cycle, climate change, water resources, and hydraulic fracturing. Please help me welcome Rob Jackson.
Thank you. Thank you, Lori. It's a pleasure to be here. Thank you all for coming, and it's nice to be back in Delaware. How's the sound in the back? Are we all right? Okay, if it starts to taper off or anything, let me know. First of all, I would love to have seen your speakers for this series, and I've seen some of them speak in the past, and others I haven't, so it would be a real pleasure to be able to catch up on that, including the 2 remaining ones. I was asked to talk tonight about unconventional resource or energy extraction, hydraulic fracturing, horizontal drilling, that sort of intersection that you're all familiar with, especially being in Ohio, a state that's grappling with a number of these issues. So I want to talk about hydraulic fracturing in a large sense of the entire process of resource extraction. We're going to focus on water because that is, of course, the emphasis of this symposium series. But then I want to throw in some air work in the end because ultimately what I'd like to demonstrate tonight is how some of the research that we do and that others in our community do can be useful to make things better. That's the motivation of the work in my group, is both to increase the basic scientific knowledge of the Earth, but also to apply the data and the information we use to improve things. So I hope that I'll give you some examples of that tonight. This was a picture I took from a helicopter. This is in the Marcellus. And this is while the hydraulic fracturing, the fracking is going on. And you're looking at generators, and there are tanks for water, and everything's being pumped underground, millions of gallons. And then obviously I want you to notice the dairy farm in the back. And I just want you to think about how your perspective on that operation might differ depending on whether you had an economic interest in that activity or not. Whether you owned your mineral rights, whether your neighbor sold his or her mineral rights and they put the well pretty close to your property line, whether your mineral rights were severed 100 years ago and you didn't even know it. And so I think some of the reason for the controversy over this approach is because people have different views, different economic interests in the process, and because it's literally an industrial activity in people's backyards. And so that's what I'm hoping to show in a photo like this. Indulge me for a few minutes. We'll talk about just a little bit about the process itself. Most of you know this information, but for the handful who might not, this is a a figure from the Energy Information Administration. It just focuses on shale resources, those that have been, where the amount has been estimated, those where people know there are shale resources there, but they don't know how much oil and gas is available. It does not show lots of other important unconventional resources, like tight sandstones that are so important in the western US and in Alberta and other places around the world. But you get a sense by looking at this at how extensive these resources are and how much oil and gas is out there depending on the price. How does it work? Well, first of all, I think the most impressive, the most amazing thing about this is the fact that we're about to pass Saudi Arabia as being the world's largest producer of oil. And if you had told people that, even in the oil and gas business in this country 10 or 15 years ago, they would have laughed at you. But that is the extent of the extraction that's gone on. How's it done? Well, two steps, neither one of which is new, horizontal drilling and hydraulic fracturing, but the combination of the two together and the very large volumes of water, the very high pressures that are used, the high intensities, I think are new. So this is how it works. Two things have to work to make this happen. So imagine you have a cake. You're after the layer of icing in the middle of that cake that's thin. And that layer of icing, in the case of a shale layer, might be as shallow as 50 or 100 feet. That layer of icing might be a mile, 2 or 3 miles down underground, in the case of a formation like the Bakken in North Dakota. So a company has to be able to identify that layer of icing. Of course, the layer of icing out there isn't normally flat. It moves. It doesn't move, but it changes in height and in thickness. And so companies use 3D seismic technology to map that, and they have to drill down, to bend that drill, and then go out through that layer and track it. Then once that horizontal drill is in place, it can be down a couple miles, it can be out a couple miles. Out a mile or more is typical nowadays. Right, then the hydraulic fracturing step comes along, where you take millions of gallons of water, sand, proppants, things that will keep the cracks open once the water has opened cracks through the shale, and then chemicals and additives to help the gas flow back to the surface, to keep microbial activity down, to change the viscosity, to do all sorts of other things. But it's that combination, the down and out, and then using that water and the constituents to crack open the rock that allows the oil and gas to come back to the wellbore and then up to the surface. And then one last thing to think about is that in many cases, these shale layers are the source of most of the conventional oil and gas fields that we've been tapping for 150 years in this country. But instead, in this case, of having a trap, a dome, an anticline, something where the oil and gas is collected, these are the rocks from which the oil and gas has been slowly migrating out over tens and in some cases hundreds of millions of years. So these are the source rocks for these formations. People knew they were there, but 20 years ago, nobody knew that we could get the oil and gas out of them economically. Right, diverse views to put it mildly. The Time magazine cover from a few years ago, an article by Brian Walsh, "This Rock Could Power the World." I pulled that one off the internet today for Ohio. Don't frack Ohio, stop injection wells. And then this sort of cartoon that's, the cat breeds Dimmock. Dimmock, Pennsylvania is one of the very first controversies over hydraulic fracturing that some of you have read about, seen perhaps. And sort of this split in communities between pro and anti-drilling. And I see this split all the time. I've walked up hundreds and hundreds of driveways of different people, different families to sample the water from their homes. And each person has a different perspective on this operation. I've seen people who are extremely happy with the way they've been treated, grateful for the revenue that they've gotten. I've seen people who are bitterly unhappy with how things have gone. So one of the interesting things for me is why that range of outcomes, and how can you nudge that range of outcomes to be more positive? But it is an issue that divides people. There are some good things going on the water side. We'll start with water, switch to air a little bit. These are some examples of some of the positive trends in the field. So one of the most positive is the increased reuse and recycling of water. This is being led in places like the Marcellus in Pennsylvania. So instead of, when we get this oil and gas out of the ground, we generate 1 trillion gallons approximately every year of pretty nasty wastewater. You have to do something with that wastewater. We'll talk about the different ways that wastewater is used or treated or handled, some good, some bad. But one way that it's increasingly handled in certain areas of the country is to take the wastewater and use it to hydraulically fracture the next well. So that reduces the amount of fresh water you have to frack that well, and it reduces the amount of wastewater that you have to get rid of somehow. But we'll talk about why that applies in some cases and hasn't so far in others. Greater disclosure of the chemicals in fracturing fluids. The transparency here is the key. It isn't true that there's no information about the chemicals in the fluids. There's a voluntary website, Frac Focus. There are state registries. Each state is different, and oil and gas operations are regulated primarily at the state level in the United States. But ultimately, greater transparency will lead to phase out of the most toxic chemicals, which would be desirable for everyone. Green completions and elimination of open wastewater pits. There are new EPA regulations going into place January 1st that will do away with some of the open wastewater pits and will require safer enclosed completion steps when the well is first coming into production. And then finally, more wells per well pad. In the old days, there was one small well pad and one well on that well pad. Nowadays, there might be a dozen wells on a single well pad. The well pad's bigger, but you've got 10 or 12 or even 15 wells going out different directions, which reduces the footprint, at least at the surface of the pad itself. So there's an older school way of drilling in the lower right. That's in Wyoming. I mean, that just kind of gives you a sense of some of the density, but that, again, is sort of the older way of doing things. All right, those are some good things. What are some of the concerns? Some of the concerns that you might have, some of the concerns that you read about or hear when you speak to people. Well, this is a partial list. Land disturbance. There are species issues out west in particular. Forest issues, road building, pipeline building. All these things disturb the surface of the earth. So do most of the other forms of energy that we use too. The amount of water that's required for hydraulic fracturing, so I won't cover land disturbance in this talk. I will cover the water and air issues. So how much water does it take? And just as importantly, how does it compare to the other ways that we generate our energy? So it's a lot of water, but how much energy do you get back out of it? Drinking water quality, the area that our groups work the most in. Disposal of produced water, and then air quality interactions. Another thing that's been in the news a fair bit recently in Ohio is induced seismicity, which can come from either the hydraulic fracturing itself, but more importantly, comes from the injection of the wastewater I talked about. So if you pump too much wastewater underground at any one place too fast, and especially if there's a fault, either it was unidentified, but if you have that fault slip, that's the kind of case where you're seeing seismic activity in places like Oklahoma that are 10 times greater than they were when they were historically. If people start having to buy earthquake insurance in an area that wasn't seismically active, it gets people's attention, even if the risk of a large earthquake is very, very, very small. I won't cover seismicity today. I'm not a seismologist, but it's primarily an issue with the disposal of water. There's nothing unique about hydraulic fracturing in that respect. It's just any time we pump large volumes of anything underground at high pressure, you can induce seismicity. All right, let's spend a minute on the water issues now. We'll start to make our way through this list of the different factors. This is work out of the University of Texas, Bridget Scanlon, whose work I like a lot. And clearly the issue of water depends on where you are. Whether you get 20 inches of rainfall a year or 40 inches of rainfall a year. Whether you're in Pennsylvania where it's relatively wet or whether you're in South Texas or Wyoming where it's dry. It also, your view of the water requirements changes depending on what scale you choose to look at it. So if you pick the biggest scale of all and ask how does the water used for hydraulic fracturing compare to other things we use, the answer is it's really pretty small compared to the two giants, agriculture and power plant cooling. So thermoelectric cooling of water to generate our electricity. All right, so those two things make up the vast majority of water that we use in this country, far more than municipal uses, for instance, in cities. So that's true at the state scale, at the country level. 1% of total water use, in some cases less than 1%. But the picture changes when that scale shrinks. So when you get down to individual counties, for instance, in some of these active areas, these are 3 plays all in Texas, the Barnett around Dallas-Fort Worth, sometimes literally right in Fort Worth. If you've ever landed in DFW, you'll see oil and gas wells on the airport. All right, when you drive into Fort Worth, there are oil and gas wells right in the middle of municipal Fort Worth. Okay, the Haynesville on the border with Louisiana, the Eagle Ford more towards San Antonio. All right, now in these cases, at the individual county level, now all of a sudden, the amount of water that's being used for hydraulic fracturing can be 10, 20, 40% of the total water use in that county. So when that's a new use added on to the county in areas that are relatively dry, it's mostly coming from groundwater, then all of a sudden it's more of a concern. So a lot of our shale resources are in pretty arid areas. That's true many other places around the world too. China, Mexico, Argentina, places that are or are going to extract this resource as well. Okay, some work that we did just recently was to try and understand how much water is actually required and how does it compare to other forms of energy. This is I won't have many tables tonight, just one or two, but you'll have two in a row. This just shows you different plays across the country. So the Marcellus, the Fayetteville, the Woodford, these are different shale plays. For oil and natural gas, the amount of water required for hydraulic fracturing here in liters and gallons. So on average, it's about 15 million liters or 4 million gallons per well. So that's a lot of water. The EUR, what's that? Well, that's the estimated ultimate recovery. This was work that I'll try and remember some people as we go along. That work was by Frank O'Sullivan at MIT. Why do you need that if you're an environmental scientist? Well, you need to know how much energy you get back out. Because you can put a lot of water into a process, but if you get a lot of energy back out, it can still be less water intensive than something else that uses less water at at sort of the one well scale or the technology. So you got to have the denominator, which is the energy out, as well as the numerator, the water in. All right, and then finally the wastewater, water intensity for fracking. This is the water intensity, so the ratio of liters of water in to gigajoules of energy out. Okay, so a lot of water is used, but not more than some other things we're used to using in this country already. So yes, it takes 4 million gallons, 5 million gallons of water per well. But when you look at the extraction and processing step for that compared to other things, other fossil fuels like coal, like oil, you look at tar sands, these are things that are all actually more water intensive than the hydraulic fracturing is. Now there are some things on that list that are far less water intensive, and the two obvious ones are solar PV, and wind power that require essentially no water. So that we do have options that are low carbon, low water, and low air pollution altogether. But then there are even some renewables that are pretty high, right? The real big one there is biofuels and corn ethanol. And that comes from the transpirational use of water, the water used by the plants themselves. That's not the plant to convert the sugars into biofuels. That's just the plant growth. And then solar concentrated can be fairly high too if you're using water to cool your mirrors out in the middle of the desert in Nevada or Arizona. All right, so yes, there's a lot of water use. A lot of other things we're already using require a lot of water as well, and we have options that are even better, like wind and solar PV. All right, switching now from the water quantity to the water quality, let's talk about where some of the possible interactions with water and water contamination can occur. And one of the take-home messages I want to leave you with tonight is that many people are worried about what's happening way down here. So the shale layer is down here in the scale of this figure off the page, if you will. And what many people are most worried about is that process of hydraulic fracturing down here, opening cracks up to the surface and connecting with that aquifer that you see. What I want you to think about instead is not to forget that, that's important, but to focus more on what's happening right at the surface and what's happening near the surface in the top few hundred feet, especially where our drinking water is primarily. And that, in my view, is what the data suggest is the most vulnerable stage for this process. So you're looking at this figure, you have a wastewater pond or a wastewater pit there up in the left. That wastewater pit can leak if the lining in the bottom of that is cut or ruptured. You can have volatile organic compounds or chemicals that move into the air and move downwind to people if that pit is open to the atmosphere. Right, you've got a stream or a lake or a river on the upper right that might be a source of water for hydraulic fracturing, might be a place where a spill can go to contaminate water. You've got chemicals on this site, like any industrial activity. My first job was with the Dow Chemical Company. And in any industrial activity, you've got to keep careful track and take care for the chemicals that are being handled, for the people on that site, and for any accidents. And then finally, the one I'll talk about next is the well integrity step. If this well has a problem, if the cement is improperly done, if the casing, the steel tubing leaks, then what's coming out of the well can move into that groundwater, or things that are found at intermediate depths can move into, up, and out. And I'll show you some examples of that as we go along. All right, one research example, when we first started doing this work was work with, continuing to be with Avner Vengosh, my close colleague at Duke. That's Nat Warner, a grad student in the upper left corner. We began working in the Marcellus because I got interested in this topic. There was no peer-reviewed science on it. I kept hearing about this process, but couldn't find any data. We went to northeastern Pennsylvania for a couple of reasons. One was that it was a very active area, and still is. The second was that unlike a lot of other parts of Pennsylvania, especially western Pennsylvania, there was not a long history of oil and gas drilling in this area, which makes, so we didn't have to deal with such an issue of legacy wells and 150 years of people extracting oil and gas. And then thirdly, and interestingly, that border that you see there is the border between New York and Pennsylvania. Now that's useful to us because, as you know, New York has a moratorium on high-volume hydraulic fracturing. Pennsylvania doesn't. So I can't go in and sample all these places before drilling occurred necessarily. So we can do that. We are doing that in some locations. But that state border, that policy difference, allows us to look at the same geology, but in very different conditions in terms of the energy extraction. So it's like a fence line comparison, if you will. All right. So what did we find? Well, first of all, there are a lot of things we didn't find. All this time, we have never found evidence of increased radioactivity that's found naturally deep underground in the produced waters. We haven't found increases in salts or metals. We haven't always had the capability to look for organic compounds, the benzene, toluene, xylene, the glycols, the things that people are most concerned about. When we have looked, we haven't seen an increase for those in people's drinking water. What we have seen in the Marcellus is an increase in natural gas constituents, methane and ethane and propane, sometimes, in a minority of cases, all within about 1 kilometer distance from the oil and gas well. So you're looking at the distance from the gas well on the x-axis at the bottom. You're looking at the methane concentration on the y-axis. The gray band is the Department of Interior's band of recommended action. So if methane is in that level in your water, they recommend considering action to vent or to get that methane out of your water. And if you're over that gray band, your water is supersaturated with methane. It can bubble like champagne. All right. So what you see here, first of all, is a natural spread of methane across that area. 80% of the houses in that area have methane in their water detectably. They have thermogenic methane, and they have that methane is natural. So that's the result of millions of years of migration of methane up through those rocks because you have those deep source rocks underlying that system. All right, so most of the people have a little bit of methane in their water. Show some specific distributions in a minute. So there's noise, there's some scatter all across this, but then you see this peak within about a kilometer. There are many more people who have very high concentrations of methane, especially these kind of supersaturated concentrations. Now, one thing that does not explain this pattern would be sort of sniffing for methane. So it's absolutely true that in the old days, a company would place a well because there was evidence of oil or evidence of natural gas at the surface, like the Beverly Hillbillies, when he shoots the ground and the oil comes bubbling up. Right? That's not what happens here. This is like imagine a checkerboard, and you're covering the real estate across a state or across an area. Right? So you have a lease. You're covering the real estate. You're not placing a well pad here because you went in there and measured high methane at the surface. That methane's, the oil and natural gas is a mile or 2 miles under the ground. All right. All right. So higher methane concentrations in a minority of cases. In some cases, really high. A fair bit of noise. Less noise when you look at the heavier constituents. This is ethane. Propane's the same way. Propane, we only find propane in detectable cases within a kilometer. All right, so why is this cleaner? This is cleaner because there are no biological sources of ethane in these environments. So you don't have methane coming from wetlands, from microbes and anaerobic aquifers underground. It's just coming from those sort of thermogenic fossil fuel-based sources. So now here you really see just the ethane found close to within a kilometer of the oil and gas wells. Okay, just a couple more graphs and we'll move on. So let's address there are a couple of criticisms of our work, all valid. One is that we don't have pre-drilling data for a lot of our houses. Absolutely true. Okay, we do now have cases of pre-drilling data and have watched that water quality change through time. We've watched people's water become super saturated in methane. But this is what you see across the landscape naturally. So what you're looking at here is a graph of chloride concentration, so a salt, and methane concentration normalized over argon 36, an atmospheric noble gas. And you see that there's a range. All the way on the far right, that square, I don't have a pointer, I'm sorry, that square at the upper right, that's a natural salt spring that occurs. That's the Salt Spring State Park. So this is an area where 100 years ago the Indians used to go and use that methane. All right, so what you see here, triangles, people who are more than a kilometer away, circles, people who are less than a kilometer away. So you see a natural spread. So when someone tells you that their grandfather in Pennsylvania could light his water on fire, those cases are true. Okay, those cases are over here. Where you see that naturally, it's not just methane, it's high salt concentrations, high chloride, often high bromide, might be high barium. So you see a family, if you will, of chemistries that go together. All natural. Another thing you see with this plot is for most of the points, there's no difference statistically between the homes that are less than a kilometer and more than a kilometer away. That's what you'd expect for the reasons that I told you. So they're statistically indistinguishable, in this case with a Chow test. This is the natural variation that you see across that landscape. Okay, then there are the anomalous samples. Okay, then there are the people who have otherwise really pure high quality water, but all of a sudden supersaturated methane in their water. These are the cases, for many reasons, not just for the data shown here, that we believe are attributable to the oil and gas drilling. And ultimately, you want to say something about the source of that gas. Now, how could you tell apart the sources? How much confidence should you have that you can tell them apart? Well, this is just one figure. That last work was Tom Dara's, Bob Pareda, our two noble gas specialists. Tom's a new assistant professor just down the road at Ohio State. So go tell him hello. Helium, in this case, over methane. Helium's a noble gas. The noble gases are useful for us because they don't react. They're not consumed in reactions. Microbes don't use them. And then there are both atmospheric and crustal sources. Right, so here's a helium plot, normalized over methane. Here's distance to gas wells again. The spread along the top is the natural spread across this space. Then you see a cluster of points, so including that salt spring that's natural there in the upper right. Upper Devonian, that's not Marcellus gas all the way down here. That's the natural gas that they used to extract 50 years ago. So there are these pockets of gas in intermediate layers at intermediate depths that have a different signature than what's found deep underground here in the Marcellus. So this is what we're comparing it to. This is what's in the Holmes water. And the point here is that there's a spread across the whole thing here, but when you're within a kilometer, you see gas that looks like the natural spread, you see gas that looks like the intermediate Upper Devonian, and you see gas that looks just like the Marcellus. So we believe that these are, the Marcellus matches are attributable to leaks in casing. So the casing that's cracked or the joints that leak. We think these Upper Devonian ones are attributable to cement imperfections, that if a well is not cemented properly, you have the rock wall, you have the casing that runs down the middle, and then you have this annulus, this donut that companies fill with cement. And if that cement is not properly done, or if there's no cement, then an intermediate pocket of gas can move into, up, and out that well into a drinking water aquifer, just like through a chimney, if you will. Right, so these are some of the mechanisms that we explored, both natural and unnatural. We've never seen evidence for this, the hydraulic fracturing opening cracks that connect to that surface or that connect to faults at the surface. There are, in rare cases, cases of number 7, where hydraulic fracturing will intersect an old or an abandoned well. There was a pretty well publicized case in Tioga County of that. where they had a geyser that shot water and methane up, and that was the intersection of a hydraulic fracturing operation and an old abandoned well. But what we think is happening is 4 and 5. So the 4 is an annulus conducted gas, so that pocket of gas is sitting there. If the cement isn't done right, it moves into, up, and out. Or if the casing is breached, number 5, then the gas that comes out there looks just like the gas that is down here. And most importantly, using the noble gases and the hydrocarbons, we believe that we can tell these mechanisms apart. Because if the gases migrate through the rock, they pass in and out of water, their solubility changes, they can fractionate for different processes, and we can make predictions and test those predictions based on the pathway. In the spirit of using the information to make things better, so here's just one figure. This was now a couple of years old, but a couple of years ago, Pennsylvania increased the casing standards, some of their setback rules and other things associated with oil and gas extraction there. We made some recommendations when our first paper came out in 2011 because of this 1 kilometer distance. So we said the presumptive liability rule should be 3,000 feet. It was 1,000 feet at that time. So the new law was 2,500 feet. The presumptive liability rule says that a company has to test your water, or at least give you the option to have your water tested within that distance before the drilling occurs. So they pay for you to get your water tested. So that protects you if your water quality changes. It protects the company from having to pay for bad water that they didn't cause. Right, so that distance was expanded. Setback distance was increased from 250 to 500 feet. Restrict drilling with 1,000 feet of a public water supply. In a perfect world, I would prefer longer setbacks, farther setbacks than that, but that's an improvement. And there is a trade-off, of course. Right, then there are other kinds of exceptions. So when things go wrong, or at least things are controversial, why might they go wrong? Well, here are a couple of examples you've probably heard about. One in Parker County, Texas, that's been in the news for about 5 years now. So in that case, and the key message of this slide isn't just about regulations, it's the best practices that different companies employ. And some companies are better and safer in how they do this process than others. So for this particular case in Parker County, Texas, there's cement down to about 400 feet. Then there's no cement all the way down to almost a mile. So in that case, it's not that you have a crack in the cement, it's that any pocket of gas is literally free to move into and up that annulus and shoot right to the surface. And you don't even have to have an imperfection in the top of the well. Any kind of crack near the surface, if that gas is under pressure, the gas is going to move out and going to find a crack and move up into the water, conceivably, potentially. So that's one example. Then, of course, the other extreme example is if you're not fracturing a mile or 2 or 3 miles underground, but a few hundred feet underground, that's a recipe for trouble too. That's the case of one of the most, if not the most controversial case for hydraulic fracturing, the Pavilion, Wyoming case. Was the first time that the EPA at least suggested that hydraulic fracturing had contaminated people's drinking water with organics and other chemicals. Right, and in that case, the hydraulic fracturing in the last 10, 15 years was as shallow as 700 feet. Right, the average drinking water in that system is about 500 feet. And it's very common to have a drinking water well down at 750 or 800 feet. Right, so that's a recipe for trouble. That's not the normal way of operating, but it happens sometimes. So best practices matter. Something I've gotten increasingly interested is in legacy wells. I'm an environmental scientist. I'm an academic. I have the luxury of thinking about years and decades, and I don't have to worry about quarterly reports and income statements and things like that. So what have we done in the past that causes problems now, and what are we doing today that might cause problems 25, 50, and 75 years into the future? So this was just out, this is work with a postdoc, Mary Kang, and working with folks at Princeton. They've been looking at methane emissions from abandoned oil and gas wells. So I took all these pictures on one property. So this was a property that has somewhere between 100 and 200 abandoned oil and gas wells across 40 acres. All right, so there's the house. There's one sort of in an upland. This, most discouragingly, this well was plugged by the Department of Environmental Protection in March. All right, so they're going to go back and do that one again, round 2. And then some of these wells are down in lowlands and sort of wetland areas, and you see these that are sort of gushing water. Let's see, I'll just give you one quick video. So here's the kind of thing you see. In this case, this is a lowland image. Sometimes those steel casings were pulled out of the ground during World War II for the steel. So that's methane coming out of that well. All right. So in terms of the legacy wells, in my opinion, we're underinvesting today in safeguarding wells for the future. So you're talking about 1 million new wells over the next 20 years or so using this operation. A state like Pennsylvania has no severance tax. Pennsylvania has an impact fee. I think Ohio, if I'm not mistaken, has a 2.5% severance tax. Let's take Pennsylvania as an example. They take in $200 million a year in impact fees. Where do you think most of that money goes? The general coffers. About $10 million a year is set aside for environmental issues. Most of that $10 million goes to current parks and such. So there's no bank account out there where all this money goes that's going to be sitting there when we need it in 10, 25, and 50 years. All right, let's finish the water part by looking at the wastewater side, just a much shorter view, if you will. I mentioned that the trillion gallons of wastewater that we generate a year from oil and gas operations in this country. Why is that water a concern, perhaps even more of a concern than the drinking water contamination or the potential for that contamination? Well, it's highly saline, especially in places like the Marcellus. In the Bakken and the Marcellus, it can be 10 times the salinity of seawater. So this stuff really, really concentrated. It can have high bromine concentrations or bromides. We care about bromides and other halogens. If those compounds get into the water and get taken into a drinking water facility, they can form trihalomethanes. These are carcinogens in water. So the water facilities monitor this. High concentrations of toxic elements, barium, arsenic, selenium, lead, metals, naturally occurring radioactivity that's found. When this water is millions of years underground, you have radioactive decay underground. You get things like radium in it from the decay of uranium. And that water, if it's brought back up to the surface and not handled correctly, can result in radioactivity being spread in the environment. And then hydrocarbon residuals. All right, what do we do with this wastewater now? Well, I already pointed out one thing, which is the last item on that list. Increasingly, some states reuse it, recycle it for hydraulic fracturing. So that's a good use. All right, some states, in fact, most of the disposal of wastewater injection in this country is deep injected. So what does that mean? So imagine you've got an old oil and gas well or an old oil and gas field a couple thousand feet down. You've pumped a lot of oil and gas out of that field. You've got a lot of open pore space, available space in that field. So now you can pump wastewater into that well and down underground. That's what we do with most of our wastewater in this country. We deep inject it. And the idea is that it's far enough underground, in most cases this is true, it's far enough underground that it doesn't come in contact with higher quality drinking water near the surface. Some states you can spray it on land. You can spray it on roads. There are half a dozen states in the US where that's still legal. Right? Not a good idea. You can treat it at a municipal water treatment plant. Not done that commonly anymore, was done earlier on in the Marcellus and other places. Those facilities are not set up to handle the volumes. They're not set up to handle the chemicals that are found in these wastewaters. So that's another thing that's not a good idea and not done that frequently anymore. States like Pennsylvania, where you don't have a lot of deep injection, have a new industry that's sprung up of private wastewater treatment facilities. And there are different levels to which you can treat this wastewater. You can exchange it with salts, you can do reverse osmosis, you can even distill it and get drinking water out of it. Even when you get pure water back out, you've got to do something with the solids and the elements that we talked about before that are left behind. But these are sort of the different suite, the different families of ways of treating it. All right, what are some examples of wastewater being a concern? Well, this is a study out of Colorado, not something I was involved with, but this is in Weld County, an area of very active oil and gas drilling out there. So they did a study looking at surface spills across this county. And they documented about 0.5%, 1 in 200 wells, or 77 specific cases affecting groundwater. That's in 1 year. That's a pretty high number. And then they also looked at the ability to remediate those spills. In most of the cases, about 80% of them, a year or two later, were back to normal. But this is one of many reasons why the open wastewater pit model for this is not a good idea in my opinion. All right, something we've documented is the buildup of radium in stream sediments below water treatment facilities. So this is downstream, if you will, of a private treatment facility in Pennsylvania. This is a facility that's followed the rules, that's always been under the EPA guidelines. They're not doing anything that's illegal or wrong. It's just the sheer volume of wastewater that's coming out of this facility is resulting in some radium building up in the sediments of this stream downstream of their outtake point, their effluent point. So what you're looking at here is radium-226 and 228 on the X and Y axis. The upstream samples, so you take samples just upstream of the plant, and they're down here in the corner, near the plant itself, downstream of the discharge, and then near the effluent discharge in the upper right. So in this case, the company that is running this facility has announced that they're going to dredge the sediments below this facility and take that sediment, and they have to dispose of that at not just a regular landfill, but at a place that can accept a higher level of radioactive waste. So this is just the kind of thing that you have to keep track of from an environmental sense and watch for. And the issue for radioactivity is very much in the solids too. Where does the solid waste, the waste go? All right, some take-home messages for water interactions. Hydraulic fracturing is water intensive as it's practiced today, but actually not more water intensive than some other things that we are currently using, which I think is a surprise to some people. And that we do have options that are low water intensity, low carbon, low air pollution, like wind and solar PV. Some primary threats to water resources come from surface spills, wastewater disposal, and one of the issues that I highlighted was water contamination in a minority of cases from poor well integrity. And I should add that we've worked in other plays like the Fayetteville Shale in Arkansas, where we found no evidence for any contamination at all. So the geology there is less fractured. Maybe the people doing the work were more careful in some cases too. And we don't know the reason for that difference. And then finally, good policies and best practices, good policies and regulations. Best practices, what the companies set, which in many cases are above the minimum rules. They can make a difference for water quantity and quality. So I want to finish my time with just a shorter example of air quality. This is the other half of the hydraulic fracturing work in my group, and you'll have to indulge me now. This is a water symposium, I know, but you got to give me the last 10 minutes. And I'll talk about some of our air work because I like this work as well. And we've been working, as many other groups have been around the country, looking at leaks, if you will, emissions from oil and gas activities. Methane is something that I've been working on personally, but groups are looking at volatile organic carbon compounds, heavier compounds, air toxics, things like that. Upstream, so at the well pad, all the way downstream to city streets. And the example I'll finish with today are downstream leaks, where we've been doing some work. How leaky are the pipelines that bring the natural gas to us? Just as in the water case, there are some benefits to a switch to natural gas, especially when you compare it to coal. Some of those benefits are listed here: less particulates, lower mercury, lower sulfur compounds. These are things that kill thousands of people in the U.S. from air quality each year. So these are compounds that matter. Right, so if you can take an old coal-fired power plant out of service and replace it with a new natural gas plant, that's a win in terms of air quality. What are some of the concerns about air quality? Well, just as we talked about water, you can have this sort of big picture sense of water not being the amount of water required not being that huge a component when you're looking at water use naturally, but at smaller scales it can be more important. The same thing's true for air. So we can have regional benefits, and yet the people who are living right by these well pads, or the people who are working on these well pads, may be exposed to some things that we need to keep track of. That's true for air too. So these are some of the concerns about air issues, the people working on the sites, compressor stations that are sort of pushing that natural gas all along, the well completions, the open wastewater pits, winter ozone formation. There have been some fascinating studies out of states like Wyoming and Utah showing air quality with ozone concentrations like you might see in downtown Los Angeles or Beijing in summer in the middle of winter, purely because there's now a new hydrocarbon source to the air over those sites because of leaks from some of the infrastructure there. Okay, the example I want to talk about is the distribution side. So this slide shows you the amount of, in this case, methane or natural gas leakage comes out of the network at different stages, all the way from getting it out of the ground to using it in somebody's home or using it for electricity generation. Okay, we'll focus on the home use for the rest of this talk. So you've got the drilling and fracturing, you've got the production step, you've got the processing, transportation, the pipeline use, and then the end users. And if you can see those numbers, the biggest number on that list is actually the downstream side of the equation, so that 0.7%. According to the EPA, that's the stage at which more of the natural gas is lost from the system. So that's percentage of the amount moving through the pipeline, or produced, if you will. So 0.7% of the natural gas that's produced leaks to the atmosphere. This is work by Adam Brandt, a colleague at Stanford. Okay, what are some examples? Well, here are some things that we've been doing. This is work with Nathan Phillips from Boston University and others. That's John Carr, who used to run my mass spec lab at Duke. So we produced the first maps of natural gas leaks across cities, at least publicly available. So imagine taking a high-resolution methane analyzer, putting it in the back of a car, putting a GPS unit on the car, putting an anemometer so you know the wind speed and the wind direction, so if you sense something, you can tell where it comes from, and then drive every block in the city of Boston, every block in the city of Washington, D.C., all 1,500 road miles in D.C.'s case, 800 road miles in the case of Boston, and mapping each leak one by one. Occasionally, when you get a high leak, you can hop out of the car and try and figure out where it comes from. Is it coming from a manhole cover? Is it coming from the curb? And places like that. So we look for the source in some cases. So what did we find? Well, here's a map of Boston. This is work that came out last year. Red is road miles driven. Yellow is, each yellow peak is a leak. Okay, so 3,300, 3,400 leaks over the 800 road miles, about 4 leaks per mile. Number one predictor of natural gas leaks? Old infrastructure. Old cast iron pipes, some of it 100 years old or more. Okay, it doesn't matter whether you're in a rich neighborhood or a poor neighborhood. It matters whether you're in an old neighborhood or a new neighborhood. All right. This work generated some quick responses. The mayor had a quote. At that time, Congressman Markey, he's now Senator Markey, had a quote. This year in July, Massachusetts just passed a new pipeline safety bill that includes accelerated pipeline replacement program for the state. Again, the notion of trying to get this old infrastructure out of the ground cost effectively and replace it with things that are better. I showed you the map of leaks. I didn't tell you where those sources of methane or natural gas came from, right? So remember all the way back in the water discussion, we talked about microbes, wetlands in landfills, in sewers, other cases. So there are a lot of potential sources in the environment and in a city. So we have to ask, once again, how much confidence do we have that we can tell those sources apart? Well, here's one of many examples we can show you, in this case using isotopic composition of the methane, so the carbon-13 signature, a stable form of carbon, and then the ratio of methane to ethane. So just like I showed you the ethane and methane plots before, ethane doesn't have these biological sources. So the ratio of methane to ethane is high when you're in a biologically derived source at the upper left there in landfills or wetlands, and low when you have a thermogenic or a fossil fuel source. And then the fossil fuel sources tend to be heavier, less negative, and the biologically derived sources tend to be lighter because microbes fractionate against the heavier isotopes. The red in this case are the actual pipeline samples. Right, so there's, again, some spread in the data, but the point here is that they cluster around the pipeline natural gas sources. We can use that kind of information to do a budget. So this is work that hasn't been published yet. It'll be coming out in the next few months, I hope. So this is a top-down inventory of all the methane leakage from Boston. This is work with Steve Wolfsey's group at Harvard and others. We have sensors outside the city, places like Harvard Forest. On the opposite side of the city, And so that when the wind blows over, when the air blows over that city, you have a background concentration of methane. And we have sensors on top of different buildings, including the Prudential, on the observation deck of the Prudential Tower there, that allows you to measure the concentration in the air and look at it build up over the city, both day and at nighttime. So it's hard to go from 3,300 leaks to what the total aggregate leak is, because you got to do 3,300 calculations, each one of which has an error associated with it, right? So forget that. Let's go from the top down. But once you get the top down, you get everything, right? You get the landfill sources, you get the sewer sources, and you get the natural gas sources. So how can you tell it apart? Well, one way you can do it is, again, to use, in this case, the difference of ethane. The change in ethane in the air, the change in methane in the axis. The blue line is what's in the natural gas pipelines. Right, so you can go online and see what the ratio of ethane to methane is in the pipelines feeding gas to Boston in real time. So if the gas in the air over Boston is coming from leaky pipelines, then it ought to look like the ratio of ethane to methane that's found in the pipelines in Boston. Right, that's what we see. So the red dots are the samples, day and night, different seasons. The red line is the slope of that relationship with some noise, of course, and you see that it's not 100%. If it were 100%, that red line would lie on top of the blue line, but it's between 80 and 90%. So almost all the methane that's building up in the air over Boston is coming from these fossil fuel sources, and maybe most interestingly, there's about 2.5 times more of that gas entering the air over Boston than the state says there is. So they're underestimating the amounts, based on this data set at least, they're underestimating the amount of methane leakage coming out of the pipelines in their state inventory. Okay, let's finish with DC, another one of my personal favorites. So the second city we did was Washington, D.C. That's the Capitol building. Capitol Hill is an old neighborhood. You're looking back east over the Capitol building. You see the leaks in that old neighborhood. Here's an app the Washington Post did based on our work, so you can plug in your address if you lived in D.C. and see what the natural gas leaks are around you. 6,000 leaks, about twice the road miles, 1,500 road miles in this case compared to 800. In the spirit of doing something about it, so it is not helpful to tell the distribution company, go fix 6,000 leaks. It's too expensive. It can cost you $1 million to put a new mile of pipe in a big city. So how might you approach it? Well, you might take the top leaks, or at least the highest concentration leaks in this case. That's what I'm showing you here. These are the top 50 concentrations that we mapped. So that might be one approach. You could take a safety-based approach. So during our first pass in Washington, D.C., in the top 20 concentrations we saw, we hopped out of the car, as I mentioned before, and tried to find the source of those leaks. All right, in a dozen of those cases, we found them, usually in manhole covers. So 12 out of 20 cases had a level of methane in the air in that manhole layer that was explosive. So that explosive limit is over 50,000 parts per million, or about 5%. Okay, so the surprising thing to me in this case was we phoned those in. 4 months later, we went back and checked them again, and 9 of them hadn't been fixed. All right, so that's an example of something we can do a better job of in terms of stewardship. And we're finishing up there. Always in the spirit of making things better, who's doing a good job? So there are companies out there that are doing a better job, cities out there that are doing a better job, and states and public utility commissions that are doing a better job. How do you know? Well, here's one way. This is a data set that just came out a couple months ago. What I did here was to take the Pipeline Hazardous Materials Safety Administration data set. So this is the federal unit, if you will, that's responsible for pipeline safety and keeping track of this stuff. They have data sets. The companies say year by year how much of their cast iron piping and old unprotected steel piping they've replaced. So you can take a data set like that and just look at the last 10 years. Don't worry about what anybody says they did. Just worry about what they actually did. So you look at the last 10 years of replacement. Who's doing the best job? Well, here's a great example, Cincinnati, Ohio. The state of Ohio, the cities, the Public Utility Commission there, companies like Duke Energy there implemented an accelerated pipeline replacement program that began in 2001. So for the last 12, 13 years, they've been chugging away at this issue, getting rid slowly but surely of these older pipelines that caused the problems. Now it's almost gone. I mean, they're done. They're 2 years away from having no cast iron piping in their system at all. Okay, so that's good. Okay. Let's look at Baltimore, Maryland, who over the last decade replaced about 6% of their cast iron piping. They're on track to finish in 2150, when all the rest of their pipelines will be 150 years old. All right, so that's not good enough. That's what they've actually done. And just to convince you, I hope that these things matter. We've already talked about Boston and DC, road miles driven, total leaks, leaks per mile. So here are two new cities we've mapped this year. So this year's work has been targeting specifically cases where we looked at places with that kind of accelerated pipeline replacement program, newer infrastructure, and said, do these things make a difference? And they do. So you look at these two cities, to be named later, and the leak rates are about 1/10. The leak densities are about 1/10 of what we see in Boston and Washington. So these policies matter. All right, why might you fix leaks, whether upstream or downstream? Here are some of the reasons. Consumers pay for a couple $1 billion in lost and unaccounted for gas each year. So that gas that leaks out of the pipelines in cities, guess who pays for that? The ratepayers do. Right, so that's one disincentive for fixing the leaks. But on the opposite side of the equation, the public utility commissions limit or cap the amount of money that companies can at least recover to repair those leaks. So in a perfect world, if I were czar, which I'm not, you would have the companies paying for the lost gas, which they don't do now in many cases, but you'd have the public utility commissions letting the companies front load repairs more quickly. And that means a little more money up front to the companies from the consumers. So there's so you can do some horse trading, if you will, to align those incentives in the place that they should be. Fixing pipes creates jobs. Fatalities are rare. Pipeline safety has improved dramatically over the last 20 years in this country. Right, half the incidents of what we would have in the 1990s. So things are getting better, but people still die every year from pipeline accidents. There are major damage from incidents. So ultimately, we want to get that as close to zero as possible. There are air quality reasons, like the ozone story I told you for rural Wyoming and Utah. Especially in warm cities, hydrocarbon sources can catalyze ozone formation and impair air quality. And then finally, yeah, there's a climate change justification for reason for doing this. Frankly, I don't care what you think about climate change. Right? There are all these other reasons that all point to the same direction for doing this. All right, I'm done. I just want to leave you with this slide, and that's to I guess ponder a bit, if you will, where our energy will come from. And we were talking at lunch today. When I was at Duke before I moved to Stanford a few months ago, I would get on a plane in Durham and I would fly north to work in the Marcellus. And as I flew north to work in the Marcellus and study some of the environmental issues associated with hydraulic fracturing, I would fly over mountaintop mines in Kentucky or Virginia or West Virginia. All right, that's a pretty destructive way to get our energy. All right, there are tar sands. You're looking at a mountaintop mine site here. There are all sorts of other things that we can do that have greenhouse gas consequences, that have air pollution consequences, that have water consequences. And then there are renewable sources that are low in all of these. So some kind of balance of energy mix is what we're going to end up with in this country. Natural gas can play a role in that balance long term, in my opinion. And based on the data, we want to be a lot farther along than we are towards the renewables end of the spectrum. There are other countries out there like Denmark that are now generating 50-60% of their electricity from wind in months. So there are a lot of issues with that transition, but there are other countries that have already moved much farther along than we have. Thank you very much. Yeah, time for questions.
Do you have time for some questions, Dr. Jackson?
You can shout them out or...
Yeah. I just have a question about why the regulation is done at the state level. And is there any possibility of federal regulation, or is this so embedded in the law and history that it's going to remain at the state level, all the regulation issues you mentioned?
Yeah. So the question back, if you can't hear, is why does the responsibility for regulation reside at the state level primarily? It's a historical fact. There are some things that are regulated at the federal level, but I can assure you, having worked with a lot of state agencies, that there's one thing that that you can do to really perturb people locally, at least at the regulatory level, is to start talking about greater federal intervention. So there are specific examples, like the source completion rules that I talked about, the ones that go into effect in January, green completions, the open wastewater pits, where economically viable. That's a great example of the feds stepping in and sort of promulgating a rule that I think will benefit everybody. And really what that rule really does is it brings the companies that are less careful up to the level of the companies that are already doing that sort of thing. All right, so it's not a radical change for some of the companies operating. That's a long answer. The short answer to your question is it's historical. It's how we do things in this country. And if you want a dogfight, propose federal regulation for every step in the process of hydraulic fracturing and oil and gas extraction.
Our mic is dead, so if you
Your mic is dead, okay.
you guys could speak loudly and you could repeat.
It would appear from the production levels that fracking for gas production for shale especially is here to stay. And I'm curious why the greatest source of pollution appears to be the fracking fluid. Why does it have to be so toxic? Why this exotic cocktail of chemicals to achieve this purpose?
So first part of the question was about hydraulic fracturing being here to stay. First of all, I agree 100% with that. I mean, we're again, regardless of what you think about anything, we're in this for the long run as a country. Other countries are going to be doing it. My motivation is to make this as safe and sustainable as possible. So the second part of the question dealt with the hydraulic fracturing chemicals themselves. Why do they have to be so toxic? Well, if you look at the list, I mean, many of the additives are not toxic. First of all, you'll hear numbers like, well, less than 1% of the constituents in hydraulic fracturing fluid are chemicals. That's true. But if you're pumping 5 million gallons of water down, and you're talking about 40 million pounds. 1% is still 400,000 pounds of stuff outside the sand and the water. Now, by no means is all that toxic stuff. And I don't drill for a living. It depends on the geology. Companies have different cocktails. I think and believe that greater transparency, as I mentioned before, greater disclosure. So a company like Baker Hughes recently announced that they would disclose all of the constituents that they use in their hydraulic fracturing operations. It's like a label on a food container. They don't tell you how much is in it, but they don't tell you, exactly how much is in the food you eat, but they do at least list the ingredients. So I think long-term, greater disclosure, greater transparency will lead to the phase-out of those toxic chemicals, and I think it'll take some of the pressure off, some of the fear away from people who are living nearby. I don't think, it's a long answer, I don't think the fracturing chemicals are the greatest risk. I think things like the compounds found in the natural deep water, for instance, are an even greater risk just because there's so much of them. I mean, yes, if you get benzene in your water, that's a bad thing. But compared to the produced water that's naturally, that volume is less than what's found naturally deep underground. But anyway, those chemicals eventually should go away. In red?
Did you see a difference in the horizontal wells that were fractured as opposed to the vertical wells that were fractured? The amount of methane that's found in the wells versus distance from the wells?
Yeah.
New York, Pennsylvania.
Okay.
And along with that, do you think that it's the materials that they're using to complete the wells, or do you think it's operator error?
I think it's a combination. So most of all the wells that we've looked at have been horizontally fractured. We do have some, but the vast majority of our samples have been in Pennsylvania. The ones we see in New York, we still see pretty much the same phenomenon. We see a minority of cases of people within 1 kilometer. So it's not the case that everybody within 1 kilometer has a problem. Most people don't. But if you're within 1 kilometer, you see a subset that have it, what we believe is an issue based on our data, but you don't see those cases more than a kilometer away. So we don't see a huge difference between just the vertical wells and the horizontal wells. We don't have a lot of data on the vertical wells to really say that directly. One example, there was a PNAS paper on well integrity earlier this year that made some of those comparisons. That paper suggested more issues with high volume hydraulic fracturing and long horizontals. But we haven't necessarily seen that. Any other questions? One over here.
Has anyone done a study on, I guess, the total energy, and you always hear about natural gas being cleaner than coal and less greenhouse gases, but I always think about all of the energy and then therefore greenhouse gas release and producing the well piping that they use, the aggregate stone they use to make the pads, to mine that, bring that to the site. I was over in Western Pennsylvania a couple of years ago. There were truck after truck, tanker trucks, taking, I assume, wastewater from the well site
Or bringing water into the hydraulic fracture.
And I just wondered if anybody's ever done a total energy carbon use of producing this natural gas supposedly is cleaner, but that's a relative term obviously too. Have you ever seen anybody do a study like that to show what the total energy to produce this natural gas is?
Yeah, so in terms of a full, so part of the spirit of the question is the full life cycle estimate of, let's separate it into two categories. The greenhouse gas, the embedded greenhouse gas emissions associated with producing the oil or gas. So there's a term, a nerdy academic term called EROI, economic return on investment, for instance. So there's the emissions associated with producing the gas. Then I'll separate the leaks, if you will, the fugitive methane emissions, which is the kind of thing I was talking about in the upstream and downstream case. So the CO2 emissions associated with producing the oil and gas, making the well pad, drilling the well are really quite small compared to the amount compared to the emissions associated with burning the oil and natural gas found underground, and pretty small compared to other operations like coal mining. Right, now the fugitive emissions case is different. We still don't know as a scientific community what the total methane leakage is. There was a paper that the Environmental Defense Fund has been organizing a lot of natural gas studies in particular. Their estimate was that about 3% leakage, so 3% of the methane that's produced leaking out anywhere in that process from start to finish is kind of the break-even point, where if you were over 3%, the greenhouse gas consequences of natural gas use would be worse than coal because methane is a far more potent greenhouse gas than carbon dioxide is. The EPA thinks it's down, instead of 3%, it's down at about maybe 1.4%. Their numbers have been bouncing around in recent years. So I think the data suggests somewhere in between. There are a number of studies, a fairly large number of studies that suggest that the inventory estimates are too low. But I think not yet enough data to suggest that you're past that break-even point. I guess I would also say that in terms of fugitive emissions, this is something we can do something about by fixing pipeline leaks, by greater sensor technology that allows you to identify which well pads are leaking the most, and dialing those leaks down. So we spend a little money to do that, develop the sensor technology to do that, but we can make a difference pretty quickly. So, any other questions or time to go home? One more, how about?
What would drive us toward wind and solar in the state or in this country? What would it take?
Well, to some extent, it's already happening. I mean, there are multiple ways to accomplish that. You could do what Germany did. I mean, and Germany now has basically the world leader in solar application, which, in terms of Germany's solar resources doesn't make a great deal of sense compared to, say, Mediterranean countries like Spain or Italy. But anyway, Germany made a policy decision to invest heavily in solar. Some states have renewable portfolio standards, for instance, so plans to mandate a certain percentage of your electricity coming from different renewable sources. What's renewable varies hugely from state to state. Sometimes it includes nuclear, sometimes it doesn't. Sometimes it includes hydro, sometimes it doesn't, only new hydro. Sometimes it includes biofuels, sometimes it doesn't. But that's another policy mechanism. Another obvious one that we're not close to getting, we came close to about 3 or 4 years ago, was a carbon price. So if we priced pollution, priced emissions from these operations, then there would be incentive for reducing those emissions. And then then the externality, if you will, the cost of that pollution would be in the marketplace. But right now, at least, we don't have a carbon price in the US. They do have a carbon price in the European Union. And so long term, a carbon price would be an option too, whether that be a tax or a market.
Well, how has a renewable portfolio standard that was put on freeze earlier this year? So we're in this very uncomfortable policy position at this moment.
So maybe are you referring to the federal level, say the incentives for state of Ohio? Okay, so I confess I'm not entirely up to date with what Ohio's renewable electricity or renewable portfolio standard is. So has it been placed on hold?
It's placed on hold, but it's written in permanent law, so it has to be retracted.
Mm-hmm.
I mean, they claim it's on a 2-year freeze, but it's written in permanent law.
Mm-hmm. Well, in other states, like California in particular, has sort of met their projections and some. You know, the renewable portfolio standards are increasingly common. I think you'll see more of them over the years, and you know, we'll see.
Yeah, and I think that this is a good note to end on and perhaps continue some conversations separately with Dr. Jackson, but this idea that we keep coming back to in this series of how local decisions and local actions can affect not only local watersheds, but global watersheds. But then also these global concerns do then have very local ramifications and ways in which you as Ohio, residents of Ohio and voters in Ohio can act at a local basis to really make differences. So I'd like to thank Dr. Jackson again and tell you guys to enjoy your break and come see us again in December.